At 12:48 in the morning on August 14th, the sky above Washington state turned briefly, unmistakably, into daytime. A brilliant blue flash tore across the darkness, bright enough to wake people from sleep and stop hundreds of partygoers mid-dance at an outdoor music festival. Then came the sound, a strange, low whooshing noise followed by a deep, rolling boom that rattled windows and set off car alarms. Within hours, NASA scientists confirmed exactly what had happened. A small chunk of an asteroid, barely 16 inches wide and weighing about 170 pounds, had slammed into Earth's atmosphere at 33,000 miles per hour and detonated with the explosive force of 10 tons of TNT, directly above one of the most densely populated corners of the Pacific Northwest. So where did this thing actually come from? And why did an object smaller than a beach ball manage to unleash that much destructive energy while burning up nearly 30 miles above the ground? To understand what actually happened above Washington that night, you first need to understand exactly what scientists mean when they use the word fireball. Every single day, Earth's atmosphere is bombarded by roughly 100 tons of space debris, the overwhelming majority of it nothing more than dust-sized particles that burn up instantly and invisibly high above our heads. Occasionally, a larger fragment survives long enough to create a streak of light bright enough for the human eye to notice, what most people casually call a shooting star. But when that fragment is large enough to shine brighter than the planet Venus in the night sky, scientists upgrade the terminology entirely, calling it a fireball, or more technically, a bolide, a specific category reserved for meteors dramatic enough to potentially explode or fragment during their fiery descent through the atmosphere. Here is exactly how researchers reconstructed the object's journey using a genuinely impressive combination of ground-based observation and orbital satellite technology. Hundreds of eyewitnesses across Washington, Oregon, Idaho, and the Canadian province of British Columbia filed reports with the American Meteor Society within hours of the event, describing everything they had seen and heard. Scientists then cross-referenced those first-hand accounts against footage captured by publicly accessible ground cameras, along with data recorded by the geostationary lightning mapper instruments aboard NOAA's GOES weather satellites, technology originally designed to detect lightning strikes from orbit, but perfectly suited to catching the brilliant flash of a disintegrating meteor as well. That combination of data allowed researchers to trace the object's path with remarkable precision. The fireball first became visible at an altitude of roughly 48 miles above the small town of Soap Lake in eastern Washington's Grant County, already glowing brightly as friction with the thin upper atmosphere began heating its surface. From there, it streaked north for approximately 36 miles, maintaining its blistering speed of 33,000 miles per hour, before finally fragmenting explosively at an altitude of about 28 miles above a location known as Sims Corner in Douglas County. That fragmentation is precisely what produced the shockwave responsible for the booming sound so many residents reported hearing, a pressure wave that traveled all the way down to ground level even though the actual explosion occurred miles above the surface. If a story like this genuinely makes you want to understand exactly why a rock smaller than a basketball can pack that much explosive punch, hit that subscribe button now, because the physics behind these atmospheric detonations reveal something most people never think about when they glance up at a shooting star. Here is the part that trips up almost everyone hearing about an event like this for the first time. How can an object weighing less than the average adult human being release energy equivalent to 10 tons of TNT? The answer comes down entirely to speed, and the almost unimaginable amount of kinetic energy packed into an object traveling at 33,000 miles per hour, roughly 43 times faster than the speed of sound. Kinetic energy scales with the square velocity, meaning that doubling an object's speed doesn't just double its destructive potential, it quadruples it. At the extreme velocities typical of meteors entering Earth's atmosphere, even a relatively small, lightweight fragment carries a genuinely staggering amount of raw energy, all of which gets released almost instantaneously the moment atmospheric pressure and heat finally overwhelm the object's structural integrity, tearing it apart in a violent explosive fragmentation event. This particular fireball happened to arrive during a period when skywatchers across the northern hemisphere were already looking upward more often than usual, since the event coincided with the peak of the annual Perseid meteor shower. That timing led plenty of people to naturally assume this dramatic fireball was simply an unusually bright Perseid streaking overhead. NASA scientists were quick to clarify that this was not the case. Careful analysis of the object's trajectory and velocity confirmed it was what researchers call a sporadic meteor, an object entirely unrelated to any known meteor shower, arriving instead from its own independent orbit around the Sun, coincidentally timed alongside the Perseids rather than actually belonging to that annual display. The shockwave produced by this fireball's fragmentation did not simply dissipate quietly into the atmosphere either. It registered on infrasound monitoring instruments positioned at several volcanoes across the Cascade Range, equipment normally used by the United States Geological Survey to detect subtle seismic and atmospheric signals associated with volcanic activity. Because these different volcano monitoring stations sit at varying distances from where the fireball actually fragmented, the shockwave arrived at each individual instrument at a slightly different moment, allowing scientists to cross-reference that timing data alongside the satellite and eyewitness reports to refine their overall reconstruction of exactly what happened and precisely where. So where did this specific fragment actually originate before it ever reached Earth's atmosphere? Objects like this one almost always trace back to the asteroid belt, that vast, sprawling region of rocky debris orbiting the Sun between Mars and Jupiter, leftover material from the earliest days of our solar system's formation, roughly 4.5 billion years ago. Collisions between larger asteroids within that belt regularly chip off smaller fragments, sending them tumbling into new, unpredictable orbits that can, over the course of millions of years, eventually intersect with Earth's own path around the Sun. When that intersection finally happens, gravity does the rest, pulling the fragment down through the atmosphere at whatever velocity its particular orbital trajectory happens to dictate, in this case, the roughly 33,000 miles per hour recorded above Washington State. Scientists studying these small, frequent impactors have grown increasingly capable of tracing not just where a fragment fell, but where in the solar system it likely began its journey millions of years earlier. Detailed velocity and trajectory measurements, like the ones gathered for this Washington fireball, allow researchers to calculate a rough orbital path for the object before it ever encountered Earth, sometimes revealing whether or arrived on a more unusual, eccentric orbit of its own. This kind of reconstruction matters for more than simple curiosity. Every documented fireball adds another data point to a growing global catalog that helps astronomers refine their broader understanding of how much debris is actually out there, how frequently it intersects Earth's orbit, and how accurately scientists can eventually predict the rare occasions when a genuinely larger object might warrant real concern. What makes this particular event genuinely reassuring rather than alarming is exactly how small and how thoroughly the object burned up before ever coming close to reaching the ground. There have been no confirmed reports of any physical fragments, what scientists call meteorites actually, surviving the descent and landing anywhere in the affected region. This matches the typical pattern for objects of this size, which almost always fragment completely and burn away entirely within the upper atmosphere, sound rather than delivering any kinetic impact directly to the surface below. That said, events like this offer a genuinely valuable reminder of just how frequently Earth actually encounters space debris capable of producing a meaningful explosive event, even if the vast majority pose no real danger whatsoever. Earlier this same year, a considerably larger meteor exploded over the northeastern United States, releasing energy, equivalent to roughly 300 tons of TNT, dramatically more powerful than the Washington fireball, yet still causing nothing more than startled residents and rattled windows rather than any lasting damage. That May event was witnessed and detected over Massachusetts and New Hampshire, traveling at more than 75,000 miles per hour, over twice the speed of the Washington fireball. A reminder that these atmospheric encounters vary enormously in both size and velocity depending on the specific orbit each individual fragment happens to follow. Just months before that, in March, another fireball streaked across a daylight sky over the eastern United States, releasing roughly 250 tons of TNT in energy and prompting eyewitness reports from 10 separate states, plus Washington, D.C. itself. Scientists tracking these events point out that significant fireball detonations of this general scale occur somewhere on Earth several times a year, though most happen over oceans or sparsely populated regions, where they go almost entirely unnoticed by the public. The Washington fireball stands out specifically because it happened to occur above a populated region during clear, dark skies, with plenty of witnesses awake and looking upward at exactly the right moment to catch the spectacle. Combine that timing with modern smartphone cameras, home security systems, and increasingly sophisticated satellite monitoring technology, and an event that might have gone almost entirely undocumented just a couple of decades ago, instead became a thoroughly recorded, scientifically reconstructed case study within mere hours of actually occurring. NASA's own Fireball and Bolide reporting system, which compiles exactly this kind of eyewitness and satellite data into a public online database, now logs dozens of these events every single year across the globe, quietly building one of the most detailed long-term records of atmospheric impacts scientists have ever assembled. For the people who witnessed it firsthand, the experience left a lasting impression regardless of the underlying science. One eyewitness attending that outdoor music festival described the entire area suddenly, becoming as bright as daytime, hearing gasps ripple through the crowd along with a strange whooshing sound, before looking up to see the night sky, an entire crowd of strangers united in a single moment of genuine collective awe. Video captured on a home security camera in Redmond, Washington, later circulated widely online, showing the exact instant the sky flashed brilliant blue before fading back into darkness. A rare, unplanned recording of an event that unfolds and disappears within just a handful of seconds. What this event ultimately demonstrates is not some looming, catastrophic threat lurking overhead, but rather a genuinely remarkable snapshot of exactly how effectively modern science can now reconstruct these fleeting cosmic encounters after the fact. A fragment of ancient asteroid debris drifting through intersected Earth's orbit at precisely the right moment to put on a dramatic, harmless light show above the Pacific Northwest. And within hours, scientists armed with satellite data, ground cameras, volcano monitoring equipment, and hundreds of eyewitness reports had pieced together almost the entire story, down to the exact altitude, speed, and mass of the object responsible. If this story left you looking up at the night sky a little differently, make sure you like this video and subscribe, because we cover the genuinely fascinating cosmic events unfolding above us that most people never fully understand until the science gets properly explained. Somewhere out in the asteroid belt right now, millions of similar fragments continue tumbling through their own unpredictable orbits, and every single one of them carries the same distant possibility of eventually lighting up someone's night sky exactly the way this one did above Washington, turning an ordinary midnight moment into a story people will still be telling years from now. Stay curious, stay informed, and I will see you in the next one.